A substation contains a coordinated set of high voltage and medium voltage equipment designed to control, protect, transform, and distribute electrical power safely and reliably. Key components include transformers that change voltage levels, circuit breakers that interrupt fault currents, and disconnect switches that provide visible isolation for maintenance. Bus bars distribute power between incoming and outgoing feeders, while instrument transformers, CTs and VTs, supply accurate signals for metering and protection. Surge arresters, lightning masts, and grounding systems protect the substation from overvoltages and lightning strikes. Additional equipment such as relays, control panels, capacitor banks, switchgear, cable terminations, and cooling systems work together to ensure the substation operates efficiently, remains safe for personnel, and maintains continuous supply to the grid. Let's discuss one by one. GIS versus AIS. GIS uses SF6 gas insulation to achieve a compact, high-reliability substation footprint suited for urban or harsh environments. AIS uses air insulation, offering lower cost, easier maintenance, and larger space requirements. The choice depends on land availability, environmental conditions, and long-term operational priorities. Circuit breakers. Circuit breakers interrupt load and fault currents using arc extinguishing mechanisms to protect power systems. They operate automatically during abnormal conditions to isolate faults. Their reliability directly supports grid stability and equipment safety. Disconnect switches, isolators. Disconnect switches provide visible isolation for maintenance and switching under no-load conditions. They lack arc quenching capability and therefore cannot interrupt current. Their role is mechanical separation of equipment for safe access. Difference: disconnectors versus circuit breakers. Circuit breakers interrupt load and fault currents automatically, while disconnectors only isolate de-energized circuits. Breakers provide protection, isolators provide safety isolation. Both work together to ensure safe system operation. Transformers. Transformers change AC voltage levels through electromagnetic induction while maintaining frequency. They are categorized as step-up and step-down based on voltage conversion direction. Transmission and distribution rely on staged voltage reduction from hundreds of kV to consumer levels. Buchholz relay. A Buchholz relay detects internal transformer faults by sensing gas accumulation or sudden oil movement. It provides alarm and trip functions for early protection of oil-filled units. Gas sampling supports diagnostic analysis. Sudden pressure relay. A sudden pressure relay detects rapid pressure rise inside transformer tanks, indicating internal faults. It provides fast tripping independent of electrical relays. This early detection limits damage and improves transformer protection. Pressure relief device, PRD. A PRD vents excess pressure from transformers when internal levels exceed safe limits. It opens automatically and reseats when normal pressure is restored. This prevents tank rupture and ensures operational safety. Rupture disc. A rupture disc bursts at a calibrated pressure level to rapidly relieve transformer overpressure. It is a single-use device that must be replaced after activation. Its instantaneous action prevents catastrophic tank failure. Difference: rupture disc versus PRD. A rupture disc is a disposable pressure burst device, while a PRD is a reusable relief valve. The disc provides one-time rapid venting, whereas the PRD opens and reseats automatically. Both belong to the pressure relief category but operate differently. Difference: rupture disc versus sudden pressure relay. A rupture disc physically vents pressure, while a sudden pressure relay detects pressure rise electrically. The disc protects mechanically against tank rupture. The relay initiates protective tripping. Both address internal faults but via different mechanisms. Thermometers and thermal relays. Thermometers provide passive temperature indication, while thermal relays actively trip equipment under overheating. Thermal relays protect motors and transformers by preventing thermal damage. Both enhance monitoring and safety. WTI and OTI. WTI measures transformer winding temperature, while OTI monitors oil temperature. Both indicators trigger alarms and cooling actions to maintain safe operating conditions. They are essential for thermal management of transformers. Oil level indicators, OLI and MOI. OLI devices show transformer oil level, while MOI uses magnetic coupling for leak-free indication. MOI often includes alarm switches for abnormal levels. Both ensure proper insulation and cooling performance. Breather with silica gel. A silica gel breather dries incoming air to protect transformer oil from moisture contamination. Color change indicates saturation and need for replacement. It preserves oil insulation quality and extends equipment life. Earth switch. An earth switch grounds de-energized circuits for personnel safety. It discharges trapped charges and provides a low-impedance fault path. Interlocking ensures it closes only when isolators are open. Difference: isolator versus earth switch. An isolator provides visible air gap isolation, while an earth switch grounds the isolated section. Interlocks prevent unsafe operations. Together they ensure mechanical and electrical safety. Bushing. A bushing insulates high-voltage conductors passing through grounded transformer tanks. It prevents surface flashover and ensures safe current transfer. Bushings are critical for HV equipment integrity. Voltage transformer, VT. VTs step down high voltages for safe metering, protection, and control. They provide accurate, isolated secondary signals. VTs enhance safety and enable precision monitoring of HV systems. Current transformer, CT. CTs step down current for metering and protection while maintaining proportionality. They isolate secondary circuits and feed relays and meters. CT secondaries must never be left open when primaries are energized. Cable sealing end. A sealing end transitions between overhead lines and underground cables. It provides insulation, mechanical support, and environmental protection. It ensures safe termination of HV circuits. SF6 to air bushing. This bushing connects SF6 insulated GIS to air-insulated systems or overhead lines. It maintains dielectric integrity across two insulation media.